5-4 gas laws, word problems, and it says to work. This is for the advanced classes 1, 2, 3, 6, 9, because usually I give you guys less work because you have to do more. But in my general class, I might have you do like a different. I'll have it written on the assignment. You might do half one day and half the other. But anyway, this is what we do if you do all of it for now. Okay, it'll be written on the assignment online to tell you. Now let's see. Here we are. Okay, gotta find my little notepad. So I've mentioned already Charles and Boyle and Gay-Lussac, their laws, and I finally have a better printout copy so you can see Jacques Charles. We'll talk about him in a moment. Okay, so the last assignment that you did, you were using the combined gas equation, PVT, PVT, and as we said, if one property is constant, like say if temperature is constant, that's Boyle's law. If the volume is constant, that's called Gay-Lussac's law. If the pressure is constant, that's called Charles' law. So those are three scientist laws, as well as the combined gas law, which is this one. So the combined, then you had they're in the notes. You'll see Charles, Boyle, Gay-Lussac. Now, for these, it's mainly the same thing you did last time, but now it's going to be in words. And I'm also going to tell you a little bit about the concept there. So, first of all, Charles, what is his claim to fame there? Actually, Charles was a balloonist. He flew balloons. There he is right there. And his law, he studied, investigated, it says, volume and temperature of a gas at constant pressure. So, they all look at P, V, and T. Chapter 5.3, not 3.5. Oh, wait, 5.4. Well, all of them look at P, V, and T. Okay? So for Charles, he said, at constant pressure, how are volume and temperature related? For Charles, I like to remember a balloon. The Charles balloon. Okay? And think about this for a minute. If you take a balloon and you change the temperature, well, first of all, let me talk about this for a moment. It's interesting. The pressure inside a balloon will always equal the pressure outside the balloon. Okay? Air is constantly, air molecules, billions and billions and billions, if you draw little dots around, they're constantly colliding with the balloon all around it. Okay? Well, the air inside the balloon is also constantly colliding around, and they also hit the outside. Well, even though I'm not drawing it too great here, what a mess. The pressure inside has to equal the pressure outside. It has to be true. It's actually Newton's third law, action, reaction. If these are not the same force, then that means if the balloon is greater, then the balloon will be expanding. Or if the air is greater, then the balloon will be shrinking. So if the balloon is not, no air can escape, but if it's shrinking or expanding, then the pressure is changing until it stops. Then, when it stops expanding or contracting, the pressure inside and outside have to be the same. So if I want to know the pressure inside this balloon, I can get like a tire pressure gauge, whatever, put it there. Or I could just simply say, well, what's the air pressure on the outside? What is the barometric pressure? Now, tire gauges actually, they only measure the pressure above atmospheric pressure, I believe. So, I'm just being real technical about that. But anyway, the pressure inside and outside the balloon are equal. Okay, just to set that straight. So for Charles, I like to think about a balloon. And I'll think, okay, what happens to V and T, volume and temperature? If I increase one, what happens to the other? Okay? So think about that little balloon, and you're young little child, you're 5 or 6 years old, you go to the Target store or wherever it is, and you're crying, and they'll make you happy. They give you a balloon. You're real happy now. You walk outside with the balloon. In the hot sun, you get into a car. The car is really hot, and the balloon, what happens? The poor balloon pops. Well, the balloon, and then the child cries. But then they go inside and they get an ice cream or another balloon and make up for it. So, okay. Well, anyway, so what happened right there? The temperature went up, and what happened to the volume? By raising the temperature, the volume also increased. Before it popped, it tried to increase probably as much as it could. You can also do this the other way. Take a balloon and put it in the freezer and just come back even like, like not even a minute, about a minute later, look in there and the balloon will be smaller. None of the air escaped, but the cold temperature slowed down the molecules there, and they got lower. It got lower pressure. We'll talk about that. It's called the kinetic molecular theory. We'll talk about that in a later lesson. That they slow down, but that makes sense. Temperature measures kinetic energy of particles of a substance. We heard that in an earlier chapter. So temperature is telling you like what is the speed of the molecules, pretty much. Okay. So if the temperature goes up, then molecules are going faster in this case until the volume expands for the balloon. Okay. Well, all right. What do you call it? If one goes up, the other goes up, or in the freezer, one goes down, the other goes down. Is that direct or indirect? Direct. So direct. So Charles' law says at constant pressure, the volume is directly proportional to and it has to be Kelvin temperature of a gas. I guess I should have put this lesson, and this scientist later, after Kelvin, if I want to be really technical about it, but it's okay. So it has to be the Kelvin temperature or it will not work. So V divided by T gives you a constant. Constant means it's the same thing over and over again. So that means if I have a graph, say I wrote down, okay, I'm going to do an experiment. I'm going to put the balloon at a temperature of 20 degrees Celsius, okay? 20, what's the volume? All right, at 25, what's the volume? At 30, what's the volume? At 40, and I go up and up and up and watch what's happening in the volume. I don't know, 1, 3, 5. I'll make up some numbers. Up 5, 7. Just say it's going up. Temperature goes up, volume goes up. Well, those numbers are not going to be true here. But anyway, let's just say that if you did that with data, if you take the first volume divided by the first temperature, it will equal a constant. That means it will equal the second volume divided by the second temperature. Or that will equal the third volume over the third temperature. And on and on and on forever. So that's where we get the law that you see is the equation for Charles' law. His law is the temperature, at constant pressure, the volume is, I gotta say it, at constant temperature, the volume of a gas is directly proportional to its Kelvin temperature. Or you can say the volume and Kelvin temperature are directly proportional at constant temperature. That's Charles' law. All right. And then there's a problem there. I think I'm just going to just tell you the scientists, all of them, and then I will do the problems at the end of that. Boyle. Let's look at Boyle now. Robert Boyle, he's the one with the hair, and here he is right there. You can see Robert Boyle. Okay, English. The other was from France. And you'll notice he was in 1660. That was a year given. I don't know if it was his birth or maybe that's probably his discovery, I guess, if I did put two dates. And Charles was 1789. So this is 120, almost 130 years earlier than Charles. So he came first. So I didn't really put them in historical order. Boyle investigated the pressure and volume of the gas at constant temperature. So for Boyle, if the temperature is constant, what's the pressure volume? For him, I like to, do I have one? Oh, I don't have it with me. That's too bad. I do have it in a box. Let me see if I can dig it out of here. Oh, no, I don't think I do. No, I don't think I do. Too bad. I thought I had one to show you. But, like a little syringe. Well, anyway, you've seen all right, so imagine you have like a syringe. I'll just try to draw a picture of one. Because while I was doing this for a little project we had, I was showing them. But let's just say that in the syringe, you put the little stopper there. Oh well. There's a little plug in there, and you put a stopper on the end. And so I have air trapped. Now, if it's trapped, it's sealed off, then when you push down on it, what's going to happen? When you increase, what am I increasing? I'm increasing the pressure, and here's the gas. So if no gas can escape, increase the pressure, and what will happen to the volume? It will get smaller. That's very easy to see. So if you increase the pressure of the gas on the gas, or that also of the gas, you cause the volume to go down. If I pull it the other way, less pressure, if I decrease the pressure, then I will increase the volume. And that will be constant temperature. Gosh, I wish I had that thing to show you. Well, I'll try in a lesson. I'll try and show you in a lesson if I do have it. I think I do, but I had some equipment here, and I think I took it back to school. I think I had it with me. Yeah, pretty sure I did. But oh well. Okay, so you can imagine that. There's another word for this. It's a better word. It's called a piston. Now, that's not a piston, but the concept is right. A piston, and usually like on an engine block, like when they say an engine, like your car engine block, it's a giant block of steel, metal, iron. That thing is really strong because what's going on inside that engine is you're exploding gasoline. If you ever lit a match and you like dropped on some gasoline, hopefully you never did that, but it would blow up. Well, that's what your car does, is blowing up inside that engine. But so since you have a giant block, it can withstand it. And what they do is they cut cylinders out in the block like this, or put them, there's little hole compartments. So a little bit of small gasoline gets inside there, and then the spark plug makes a spark on it. When that gasoline burns, it goes from a small bit of liquid to a giant volume of gas. That's one of the amazing things about the gas law chapters. It explains to you why changing from a liquid to a gas is so incredibly powerful. We can harness that energy. If I had, well, I do have this with me, it's not much to say, but if I just had a small bit, like even about 20 milliliters of water, let me think about that. Yeah, that's about right. 20 milliliters of water right there. If I filled it up to 20 right there, that's a smaller bit of water. If I were to turn all that and evaporate it, like immediately, just take it evaporate into gas, that would be quite dangerous. Steam, like you know what a steam engine, like it pushes steam, water goes to steam and pushes out, kind of like the same idea, like a cylinder or somewhere. It pushes it, and that gets translated into motion for the axles and power and all that to move the train. Same thing with a car. But what we're going to tell you, that 20 milliliters, it would take up a volume that would be about like 20, more than like maybe 25. I'll put it like that. Maybe 25 liters. I'm going to try and draw that and guess that's about a 25 liter balloon. So a small bit of liquid, water right here, just by turning it into steam, it goes from this volume to that. So if this small liquid were in here and you suddenly turn it to steam, so what happens is in a cylinder, well, we'll start, well, I can't draw it so good. It's like, let's say this thing's all the way down, almost all the way down. Okay, and you put the water in here or whatever, it converts to steam, boom, it's going to push that thing up with incredible force, all right? Now, that's only water changing to steam. That's nothing compared to gasoline exploding. Gasoline exploding would do, it's incredible how much force you get out of that. So anyway, I thought I would tell you that, add that little bit in to let you see kind of a technology application of this. But anyway, so for Boyle, imagine you have like a little syringe, and you increase the pressure, and the volume gets smaller, or decrease pressure, the volume gets larger. So if one goes up, the other goes down. Is that direct or indirect? Indirect. Good. So Boyle's Law says at constant temperature, the pressure of a gas is indirectly proportional to the volume of the gas. Now, you can also say inversely if you want to use that word. The pressure and the volume are inversely proportional to each other at constant temperature. Now, when you push it down real fast, actually, just the friction there, it might say, well, it might heat up for a moment, from this hitting the side. It might get a little bit warm, but then hold it in place, and then for the next moment, it'll adjust. So the temperature is considered to be constant in that experiment. Okay, so that is Boyle's Law. Now, so when they're indirect, to get a constant, you don't divide them, but you multiply them. So P times V will be a constant. So again, if you got a bunch of data, and you say, okay, I'm going to put a pressure of one. You could actually, instead of pressure, you could actually use weight and force if you wanted to do this in the lab. Say, I'm only going to put, like, say, 1 pound of force on it. And what's the volume? Okay, pressure, volume. Now, I'm going to put 2 pounds of force, what's the volume? And 3 pounds, or 4 pounds, or 5 pounds. And the volume will go down like 10, 8, 6, 4. Well, it's 4, 2. I'm just making up numbers. The point is, as the pressure gets higher, the volume will get smaller and smaller. So if I did that, P1 times V1 will always equal P2 times V2, etc. Now, I made these numbers up, so they're not going to work, but I just wanted you to get the idea that P1 V1 is P2 V2 or P3 V3. Any pressure times its accompanying volume will always multiply to give the same thing. So that one is Boyle's Law. And then Gay-Lussac's Law, it's not mentioned in a lot of books because there's another more important discovery that he made, and also dealing with gases, something he noticed about chemistry. So this is his law of I don't know. There might be a name more there might be a better name for this, but anyway, and there he is right there, not Jacques Charles, Joseph Louis Gay-Lussac. All right, from France also. Now, he talks about pressure and temperature at constant volume. So for Charles, I remember the balloon. For Boyle, think about the syringe or piston. And then for Gay-Lussac, think about an aerosol can. Like, say if you have an aerosol can, and you see like you have spray paint in there, or hairspray, or deodorant, or whatever it is. Okay? Well, inside there is a liquid that is very volatile, that evaporates very easily. In other words, it's a liquid like an alcohol, or I'm not sure what exactly they use in there, but you can almost kind of smell it as well. And when you shake it up, it will turn to gas. So like I just told you a moment ago, that liquid turning to gas, boom, suddenly it's a big pressure inside. Okay? So this will build up pressure really easily. Now, then they put in there, along with that propellant, they put in like whatever, the deodorant or the hairspray or the spray paint liquid. And so that propelling, the pressure build up inside pushes out the other stuff. And so when you spray it, you notice that odor. Besides the paint, you notice some other kind of odor besides the paint in there. And that's you're smelling probably the aerosol, whatever the propellant chemical they use. I don't know what that is. But all right. So for this one, it always says on these cans, do not store, do not incinerate, or do not put in a fire, do not store in high temperatures, because what will happen? Temperature and what is constant here? Can you tell which one is going to be constant? It should be the volume. So your volume doesn't change. So in this case, if I increase the temperature, what's going to happen to the pressure inside? Well, again, remember the molecules of gas, they're going to move faster. I just told you that a moment ago from the other one. And we'll talk about kinetic molecular theory one day to kind of get that again. But so that means the pressure goes up. So at a higher temperature. So that means if that's true, if you have the hairspray, deodorant, if you put it in a refrigerator, make it really cold, shake it up, put it in the refrigerator, it's not going to spray as forcefully. If you had another one that you had in the warm water or warm container, maybe water, but warm air, it would spray faster or more forcefully. Okay, so what he says is the pressure of a gas at constant volume. The pressure of a gas is directly proportional to its Kelvin temperature. And it has to be in kelvins, the temperature, for this to be true. So, just like in all the other ones, P times T is a constant. And maybe I didn't mention it here, I mentioned it in an earlier video. K, that letter is just a general letter for constant used in physics and science. It's from the word Konstant, a German word, like constant with K. PT is a constant. So, no, bad fella. Look at that. Wait, P divided by T is a constant. Sorry about that. How in the world did I? Bad. Okay, that was a mistake. But oh well, I'll keep it there to show you that I can make a mistake there too. But remember, when they're directly proportional, both go up, both go down. Directly proportional, you divide. When they're indirectly proportional, you multiply. So P divided by T is a constant. So P1 over T1 equals P2 over T2, etc., and on and on. So, you now have 4 gas laws to choose from, and you should know which is which: the combined gas law, Charles' law, Boyle's law, Gay-Lussac's law, and you ought to know how to state their laws. What is constant? What do the laws say? I want you to know that. Who says, at constant temperature, the pressure of a gas is indirectly proportional to the volume of the gas. Be able to say that. Okay, now the calculation stuff. Let me see here. Where I put my notes for this one. Do I have time to go through? Or I've got another thing I got to do here too as well. I'll have to make a second part. I'll put the calculations on a second part for you. And it won't be too long, so sorry about that.